Have you ever wondered why global weather suddenly flips every few years? I'm Anita, and welcome to a brand new episode of Haven Cadre. Massive droughts hit Australia, while historic torrential rains flood South America. The secret driver behind these global weather disruptions is a natural climate cycle. Scientists call this climate phenomenon the El Niño Southern Oscillation, or ENSO. ENSO swings continuously between two dramatic opposite climatic phases. El Niño brings significant ocean warming to the eastern equatorial Pacific. Meanwhile, La Nina is the exact opposite cooling phase of the same ocean cycle. Today, we will examine the exact physics of how this engine operates. To understand El Niño, we first must look at normal ocean conditions. Under neutral conditions, strong trade winds blow constantly from east to west. These powerful winds pile up warm surface water near Asia and Indonesia.
Because warm water accumulates in the west, sea level is actually higher there.
In fact, the ocean surface in Indonesia is up to 50 centimeters higher than Peru. As surface water moves west, nutrient-rich cold water wells up off South America. Rising warm air in the west creates intense tropical rainstorms and thunderclouds. That complete atmospheric loop is known as the Walker circulation cell. But every 2 to 7 years, this stable system suddenly breaks down. The trade winds weaken significantly, and sometimes even reverse direction. Without strong winds pushing west, warm water sloshes back eastward toward America. This massive eastward movement of warm water shuts down cold ocean upwelling. As a result, the eastern Pacific sea surface temperature rises dramatically. Thunderstorms and heavy rain move eastward into typically arid regions. Warm water releases immense heat energy directly into the upper atmosphere. Meanwhile, western Pacific countries like Australia suffer severe rainfall shortages. An official El Niño occurs when sea temperatures stay elevated for 5 months. Now, what happens when the climate pendulum swings to the opposite extreme? That brings us to La Nina, where standard trade winds become supercharged. Trade winds blow much stronger than normal, driving warm water far into the west. This intense wind force pulls freezing, nutrient-dense water up from the deep ocean. Marine ecosystems thrive along South America due to rich plankton upwelling. Central Pacific Ocean temperatures plunge well below long-term climate averages. Atmospheric convection shifts even further westward toward Indonesia and Asia. Consequently, Southeast Asia experiences severe monsoons and widespread flooding. La Nina reinforces hypernormal conditions across the entire tropical belt.
Why should someone living thousands of miles away care about Pacific waters? Because heat shifts in the Pacific disrupt planetary atmosphere flow patterns.
Meteorologists call these distant climate connections atmospheric teleconnections. During El Niño, the Pacific jet stream extends and shifts further south. This brings wet winters to the southern United States and mild weather up north. El Niño creates high wind shear over the Atlantic, suppressing hurricane formation. Conversely, La Nina weakens Atlantic wind shear, leading to active hurricane seasons. Global food prices, agricultural yield, and water security hinge on these cycles. From grain harvests in Brazil to winter heating demand in Europe, ENSO shapes lives. How do modern climate scientists predict when the ocean phase will switch? Meteorologists track specialized oceanic indices like the Oceanic Nino Index. Array systems like the Domino network measure deep water heat content directly. Subsurface heat anomalies often give us months of early advance warning. Advanced supercomputer models combine ocean temperature and wind velocity data. These predictive models allow nations to prepare for impending floods or droughts. While forecasting accuracy has improved immensely, ocean physics remain complex. Small atmospheric fluctuations can speed up or delay an incoming phase transition. El Niño and La Nina remind us how deeply interconnected Earth's systems are. What begins as a subtle wind shift in the tropics impacts millions of lives. Understanding ENSO empowers humanity to adapt and build global weather resilience. Subscribe to stay curious and join us for more deep dives into Earth science.